Matrix operations are fundamental tools in mathematics, and they serve as the backbone for many practical computations and transformations. In this lesson, we will explore four key matrix operations: addition, scalar multiplication, matrix vector multiplication, and matrix multiplication. Let us begin with matrix addition and subtraction. Matrix addition and subtraction allow us to combine or differentiate information represented in matrices. To add or subtract two matrices, they must have the same dimensions. The operation involves adding or subtracting corresponding elements of the matrices. For example, consider two matrices, A and B. Matrix A has entries 2, 4, 6, and 8, while matrix B has entries 1, 3, 5, and 7. When we add these matrices, we perform the operation 2 plus 1, 4 plus 3, 6 plus 5, and 8 plus 7, giving us a new matrix with entries 3, 7, 11, and 15. Similarly, subtracting these matrices results in a new matrix with entries 1, 1, 1, and 1. Next, let us discuss scalar multiplication. Scalar multiplication involves scaling an entire matrix by a single number called a scalar. Each element in the matrix is multiplied by the scalar. For instance, if we have a scalar of 3 and a matrix with entries 2, 4, 6, and 8, multiplying every element by the scalar gives us a new matrix with entries 6, 12, 18, and 24. Now, we move on to matrix vector multiplication. This operation allows us to transform a vector using a matrix. To perform this operation, we compute the dot product of each row of the matrix with the vector. For example, let us take a matrix with entries 2, 3, 4, and 5, and a vector with entries 1 and 2. To compute the result, we multiply 2 by 1 and add it to 3 times 2 for the first row. For the second row, we multiply 4 by 1 and add it to 5 times 2. The resulting vector has entries 8 and 14. This process demonstrates how matrix vector multiplication transforms a vector. Finally, we arrive at matrix multiplication. This operation combines two matrices to form a new matrix. Matrix multiplication is only possible when the number of columns in the first matrix matches the number of rows in the second matrix. To compute the product, we calculate the dot product of each row in the first matrix with each column in the second matrix. For example, if we have matrix A with rows 1, 2, 3, and 4, 5, 6, and matrix B with columns 7, 9, 11, and 8, 10, 12, we calculate the product by taking the dot products of the corresponding rows and columns. The resulting matrix has entries 58, 64, 139, and 154. In summary, matrix operations are foundational for mathematical transformations and computations. Addition and subtraction allow us to combine and differentiate matrices. Scalar multiplication scales a matrix by a single number. Matrix vector multiplication transforms vectors using matrices, and matrix multiplication combines matrices into new ones. These operations enable us to perform and understand complex computations and transformations, forming the basis for applications in fields such as machine learning and computer graphics.